Good afternoon, everyone. My name is Eber, and today we'll present our research and optimized approach for academic resource timetabling. This project is the result of the joint work between myself and my advisor, Professor Sérgio Freitas, both from the University of Brasilia. We have focused on developing a solution that improves the scheduling process in higher education institutions by addressing complex constraints and optimizing resource allocation. Scheduling in higher education is a challenging task. Universities must balance multiple constraints, such as rooms availability, instructor preference, and student needs. The goal is to ensure an efficient schedule that accommodates these requirements without conflicts. These constraints can be divided into hard constraints, which must be strictly satisfied, and soft constraints, which are more flexible but still enhance the schedule's quality when met. In addition to managing these constraints, institutions must also deal with the complexity of coordinating thousands of events, rooms, and stakeholders within a limited number of time slots. This makes the scheduling problem not only time-consuming but also computationally difficult. The main objective of our research is to develop a model that leverages constraint programming, specifically using CP6 software to create efficient academic schedules. The model is designed to optimize resource allocation while ensuring that the necessary institutional and pedagogical requirements are met. To validate our model, we tested it using real dataset from the University of Brasilia, a large public university in Brazil. With approximately 44,000 undergraduate students, 9,000 graduate students, and 2,500 faculty members, the university offers over 11,000 course sections and processes about 400,000 course enrollment each semester. This provides a complex environment where multiple scheduling constraints must be respected simultaneously, making it an ideal case to evaluate the robustness of the model. Our literature review focuses on identifying the most common algorithms used in academic timetable and scheduling problems. Through a systematic review of key databases like ACM, IEEE, and scalable, we found methods that have been applied successfully in solving complex scheduling problems. However, based on the specific needs of our case study, we selected constraint programming using CPSAT due to its strong ability to handle large-scale and highly constrained problems. CPSAT allows us to model both hard and soft constraints, providing the flexibility required to accommodate the diverse and oft conflicting requirements of academic institutions. This choice is well supported by recent studies, which emphasize CPSAT's effectiveness in solving complex combinatorial problems. The methodology involves building a web-based system with three components. The customization module allows users to adjust schedules. Integration ensures compatibility with academic management systems, and the processor allocates events based on constraints. We use Flask for interface and Python for constraint programming. Additionally, the system provides real-time feedback to users as they interact with the schedule, allowing them to see immediately whether any constraints are violated when adjustments are made. Our model incorporates both hard and soft constraints to ensure the feasibility and quality of the generated schedules. Hard constraints are non-negotiable and must always be met for the schedule to be valid. For example, ensuring that two events are not scheduled in the same room at the same time is a critical hard constraint. On the other hand, soft constraints address preferences that improve the quality of the schedule, such as assigning a preference room or scheduling class at times that suit instructor preference. The objective of our model is to minimize penalties by optimizing the schedule to satisfy as many of these preferences as possible, creating a balance between hard requirements and desirable outcomes. Our experimental results are based on 11 real-world datasets from the University of Brasilia, each representing different complexities in terms of number of events, rooms, and constraints. The CPSAT software was able to handle all datasets and find optimal solutions for each, demonstrating its effectiveness in dealing with both small and large instances of the scheduling problem. The smaller datasets, such Dataset 1, which contained 11 events and 6 rooms, required only about 4 seconds to find the first solution, highlighting the solver's efficiency with simple cases. As the complexity of the dataset increased, the time to find the first solution also grew. For example, dataset 11, which involved 1,473 events and 188 rooms, took significantly longer, over 7,825 seconds to compute the first solution. This shows that while CPSAT is capable of scaling to larger datasets, the computational time becomes a challenge as the problem size increases. Despite this, the solver consistently provided higher quality solutions that respect both hard and soft constraints. These results highlight the scalability of our approach and demonstrates that it can be applied to real-world academic scheduling scenarios, even large complex institutions. Now, looking at the time required to find the optimal solution across different datasets, we can see a clear trend in Figure 1. The horizontal axis represents the dataset number, and the vertical axis shows the time in seconds that the CPSAT solver took to find the optimal solution. As expected, smaller datasets, such as dataset 1, required very little time, only around 4 seconds to find the optimal solution. However, as the datasets grow in complexity, the solver takes significantly longer. For example, for dataset 11, the solver took over 50,000 seconds or roughly 14 hours to find the optimal solution. This demonstrates that while the model is highly effective at handling complex scheduling problems, the time required to find optimal solution increases considerably with the size and complexity of the dataset. This result highlights the scalability challenges when dealing with larger instances, but also confirms the robustness of the CPSAT in ensuring optimal solutions even under these conditions. In this slide, we will discuss the impact of pre-solving techniques on the model's performance, particularly in terms of reducing the number of variables and constraints. As seen in Figure 3, which shows the number of variables before and after pre-solving, the initial model for larger datasets contained millions of variables. However, after applying pre-solving, this number was significantly reduced. For example, in dataset 11, the number of variables dropped from over 25 million to about 18.9 million. This reduction is crucial as it simplifies the model and allows the solver to handle larger datasets more efficiently. In Fig 4, we observe the significant impact of pre-solving on the number of constraints in the model. For example, dataset 11 starts with over 25 million constraints, which were reduced to around 660,000 after applying pre-solving techniques. This reduction eliminates redundant or unnecessary constraints, allowing the solver to focus on solving the most relevant ones. By reducing the number of constraints, the model becomes more efficient, especially for larger datasets. This optimization enables the CPSAT solver to handle complex scheduling problems more efficiently, ensuring scalability without sacrificing solution quality. In conclusion, our study demonstrated the effectiveness of using CPSAT solver for academic resource timetabling. By applying constraint programming, we were able to handle complex constraints and optimize scheduling in a real-world academic setting. The results show that our approach provides efficient and scalable solutions, even for large datasets with multiple constraints and preferences. We aim to extend this model by integration gamification and machine learning techniques. This will allow for enhanced user interaction and further customization of the schedules, aligning them with more closely with institutional needs and pedagogical strategies. Additionally, we plan to explore the composition strategies to improve performance in handling even larger data sets. This could provide a more flexible and dynamic scheduling system, improving both administrative efficiency and the educational experience. Thank you all for your attention. I hope this presentation has provided insights into our approach to optimizing academic scheduling using CPSAT. If you have any question or would like to discuss the potential application of this model further, I'll be happy to answer them.